The quantity of intelligent civilizations in the cosmos equals the count of habitable planets, multiplied by the likelihood of life's inception, multiplied by the likelihood of intelligence evolving among living beings. If you rise now and observe yourself in the mirror, you'll notice imperfections in matter. To comprehend this, we must dispel a common misconception about matter, such as water. When water freezes, it transforms into ice, assuming a crystalline form. Since childhood, many of us genuinely believe that ice crystals, snowflakes, or patterns on frozen surfaces exemplify spontaneous symmetry in nature, showcasing the emergence of harmonious structures amidst natural disorder. However, this belief is mistaken. In reality, it's quite the opposite. A crystal formation doesn't signify emergence, but rather a breakdown of symmetry. This occurs because water possesses greater isotropy, meaning it's more uniform and symmetrical in all directions compared to ice. As water crystallizes, its atoms self-organize into specific patterns. Notably, the space occupied by the crystal loses its symmetry and adopts periodicity through a particular algorithm. Essentially, the crystal disrupts spatial uniformity, generating repetitive patterns in specific directions. Observing our universe, you'll observe a similar phenomenon. The universe demonstrates considerable homogeneity. Your location doesn't significantly affect what you observe. Looking out the window at the starry sky, you will find that the part of the universe we can see is a good sample. If you were looking out the window while on the other side of the galaxy, you would see roughly the same thing. But if the universe is so homogeneous, then what are you doing here? Just as ice breaks the symmetry of water, galaxies, stars, and planets break the symmetry of the universe, but nothing breaks it by its existence as much as a human being. Stanislaw Lem, in his monumental work, The Summa Technologiae, asks, is our civilization ordinary or exceptional? Do we conform to the norms of development accepted in the universe, or do we represent an aberration, an ugliness? We grasp the mechanisms behind water crystallization and the formation of various cosmic entities. However, let's not delude ourselves. The origin of our existence remains far from clear. Consider this. Mentally transport yourself billions of light years in any direction and survey your surroundings. The universe presents itself as profoundly inhospitable for human life. Is there even a remote spot beyond Earth where survival is possible? Perhaps our existence hinges on an extraordinarily fortunate or unfortunate coincidence, a probability extending across the entire universe since its inception. This notion is posited by paleontologist Peter Ward and astronomer Donald Brownlee in their book, Rare Earth. In their book, the authors argue that complex life is a highly improbable, rare, or even isolated occurrence, necessitating extraordinary astrophysical and ideological coincidences. This video draws heavily from their work, particularly the unique Earth hypothesis, which the book thoroughly elaborates upon. How many times have you heard that Earth is the most ordinary rocky planet in a typical planetary system, located in an unremarkable region of one of countless galaxies? Carl Sagan and Frank Drake were fond of saying that. They, along with many other scientists, believed that given the apparently unremarkable nature of our environment and the abundance of Earth-like planets, the universe should be overflowing with life. This viewpoint is encapsulated by the principle of mediocrity. However, what if we consider the opposite perspective? What if we entertain the idea that our Earth is fantastically unique? What if the solar system isn't a typical cosmic arrangement, but an unimaginable rarity? Could it be that our entire galaxy, too, isn't just an ordinary case? What were the conditions necessary for the emergence of humanity, a peculiar form of matter? From the perspective of advocates for the unique Earth hypothesis, everything isn't as straightforward as it might seem. Supporters of this hypothesis contend that a planetary system conducive to supporting complex life must resemble the solar system to some extent. Many believe that the so-called Goldilocks zone, where conditions are neither too hot nor too cold for life to emerge, is nearly the sole requirement for life's origin on a planet. It's also referred to as the habitable zone, a region surrounding a star where conditions on the surface of orbiting planets will support liquid water, a crucial element for life, serving as a solvent in numerous biochemical reactions. Earth's orbit around the Sun is notably circular, ensuring it remains within a suitable range, neither too distant nor too close. Many believe that if you find rocky planets in space that orbit their stars in the Goldilocks zone, life on those planets would almost be an inevitable consequence. However, according to proponents of the unique Earth hypothesis, mere placement within a star's habitable zone isn't sufficient for life to flourish. They argue that our entire solar system benefits from being situated within the habitable zone of our galaxy. Our solar system revolves around the center of the galaxy at a rate of one full revolution in about 235 million years. That is, since the oceans appeared on Earth, it has traveled that entire distance 17 times. Since the first reliable traces of life, 15 times. Since the first multicellular organisms, about 7 times. Despite the vastness of the galaxy, it harbors many threats that could prove deadly for our comparatively tiny solar system, particularly over such extensive periods, but the living matter is still here. You see, however, it must be recognized that most regions in any galaxy are inhospitable to support complex life. As you get closer to the galactic center, the destructive effects of X-rays and gamma rays increase. These harmful radiations are emitted by black holes and neutron stars that proliferate closer to the galactic center. Proximity to the galactic center also increases the frequency of nearby supernova explosions. Although galaxies boast many stars and even more planets orbiting those stars, the assumption that life must thrive throughout the Milky Way is flawed. Most stars are concentrated near the galactic center, which is a natural result. In addition, the greater density of stars near the center or in spiral arms leads to greater gravitational perturbations. Consequently, even if a planet orbits its star at an optimal distance, this delicate balance can be disturbed by the gravitational influence of neighboring stars, or something worse. In general, being too close to or too far from the galactic center presents challenges. Moving away from the center reduces the metallicity of stars, crucial for forming Earth-like planets. Recent research suggests the galactic habitable zone spans about 79 kiloparsecs from the center, encompassing only around 10 of Milky Way stars. Some studies suggest only 5% of stars are suitable for life's origins, but the most important thing is timing. A life-sustaining planetary system must maintain stable conditions for billions of years to allow for the development of complex life. Ideally, a star hosting life should have a nearly perfect circular orbit around the galactic center. Additionally, its rotation rate should synchronize with that of the spiral arms, minimizing its passage through dense star clusters. The solar system resides precisely within the habitable zone of the entire galaxy, benefiting from the Sun's nearly perfect circular orbit around the Milky Way's center, which aligns closely with the galaxy's rotation period of about 235 million years. Our planet is lucky to be in the Goldilocks zone of its star system, which in turn is lucky to be in the Goldilocks zone of its galaxy. But that's not all. Moreover, our entire galaxy represents a rare occurrence. At 10 billion years old, the Milky Way has largely avoided collisions with other galaxies, resulting in its unusually tranquil and subdued nature. Only 7% of all galaxies share this characteristic. As you can see, even on such a huge scale, there are many nuances to reckon with if we are to understand how unique our fate is. However, most of the mysteries and unthinkable coincidences are not out there, but right here within our solar system. When observing the stars, we envision them resembling our sun if we were closer, although we acknowledge their potential differences such as in size. However, it's estimated that over 50 of star systems in our galaxy consist of at least 2 stars. In half of these cases, approaching these stars would reveal conditions similar or even more extreme. For instance, the polar star, renowned for aiding navigation, is actually part of a triple star system. While double, triple, and similar star systems are visually striking, they are likely inhospitable. The stability of planetary orbits in multi-star systems remains uncertain, requiring precise conditions for planets, even uninhabited ones, to exist harmoniously. This immediately eliminates more than half of the stars as potential candidates. Furthermore, our sun possesses unique qualities, and even single star systems don't guarantee stability necessary for life to evolve. The sun exhibits a minimal variation in luminosity, merely 0.1%, Although often touted as a common star among countless others, no solar twin stars have been discovered to date concerning luminosity, size, temperature, age, and metallicity. Mind you, proper metallicity is needed for the formation of the protoplanetary disk from which planets form, and for the small change in luminosity of the star. Is the Sun an absolute ideal? There exist numerous variations. For instance, larger stars boast a broader habitable zone, increasing the likelihood of life's origin based on temperature. However, larger stars emit more powerful ultraviolet radiation and consume their fuel more rapidly, transitioning into red giants sooner. Consider Betelgeuse, a favorite star, nearing the end of its life at a mere 10 million years old. By comparison, the Sun is 500 times longer. Ignoring the radiation, even the simplest life near supermassive stars probably won't have time to develop. But then there are red dwarfs. They emit less radiation, and they live longer than the Sun. A red dwarf with 10% of the mass of the Sun will burn for 10 trillion years, an inconceivable amount of time. Furthermore, red dwarfs never become red giants. That's true, but only red dwarfs are quite cold. Their temperatures are just above the temperature of the filament in a light bulb, about 3,000 degrees Celsius. And they're very dark. Some red dwarfs emit 10,000 times less light than the Sun. So, a planet with the potential to develop complex life needs to be very close to such a star. And that seems cool. But there are at least two problems. The first is that a planet so close to a red dwarf will almost inevitably fall into a tidal trap and begin to revolve around the star, turning to it forever only one side. It's called tidal entrapment. It's what happens between the moon and the Earth. So, it will always be monstrously hot on one side of the planet and monstrously cold on the other. The stellar wind, which in red dwarfs is not particularly weaker than the solar wind, will leave no chance for life to develop in the terminator zone. The terminator zone is that strip between light and darkness, where the temperature could theoretically be comfortable. Now, look at the planets in our solar system. Do they look normal? Is there anything unusual about them? What about their positioning? Is this even a typical arrangement of planets and planetary systems in the universe? We have 4 small rocky planets, followed immediately by gas giants. That must be quite common. Well, it's not. We actually have a very strange planetary system. First, it has the strongest variation in the characteristics of the planets, from tiny Mercury to Saturn to Jupiter. In most planetary systems in the universe, the planets are not very different from each other. Most planetary systems in space near a star have super-Earths, several times the size of Earth. But here, we have only a few small, rocky planets in the inner region of the solar system, and none inside Mercury's orbit. Secondly, gas giants the size of Jupiter or Saturn are quite rare and occur in only 10 of planetary systems. And these few very rarely have stable, almost circular orbits so far from their star, and we have as many as 2 of them with fairly circular orbits and at a considerable distance from their star. We still don't really understand how this configuration of the planets in the solar system came to be. All sorts of complex computer models are being derived, but there is no consensus yet. Some people will irritably ask, well, what does this arrangement give us? Lots of things. Unlike most super-Earths in space, the size of the Earth is optimal. A planet that is too small, among other things, cannot maintain an adequate atmospheric layer, causing its surface temperature to be low and variable. Oceans will simply not be able to appear. A planet that's too big, on the other hand, will retain a very dense atmosphere. Wait, so our neighbor Venus, while smaller, has an atmosphere 92 times denser than Earth's, which makes its temperature about 462 degrees Celsius. That's true, and perhaps the early Earth once had a similar atmosphere, but then may have lost it in the catastrophic impact that formed the Moon. That impact subsequently allowed the Earth to acquire an atmosphere with optimal parameters. Its density perfectly compensates for daily temperature variations. The ozone layer formed protects the Earth's surface from ultraviolet light. Nitrogen and carbon dioxide are in the right ratio for the emergence of life, precipitation necessary for the water cycle, and so on and so forth. But we digress. It is this distribution of planets, where the gas giants are on the outer side of the planetary system, that gives the advantage of a shield against asteroids. Look at Jupiter. It is often underestimated compared to Saturn, actually 2.5 times more massive than all the other planets combined. The considerable mass of this gas giant probably prevents the theoretical Oort cloud, which contains trillions of comets and is estimated to have a mass of 2 Earth masses, from posing a threat to Earth by keeping it at a great distance beyond the orbit of Neptune. Oort cloud objects are thought to have originated near the Sun, but were expelled by the gravitational influence of Jupiter and other gas giants early in the formation of the solar system. In addition, any debris from the periphery of the solar system trying to move toward its center is likely to collide with one of the gas giants, increasing the risk of collision. 30 years ago, Jupiter intercepted a comet measuring 20 kilometers in diameter, fragmenting it before impact. Had Earth encountered such an object, its outcome would likely have been catastrophic. Jupiter routinely attracts potentially hazardous space debris. In 2009, an object left a mark resembling the size of the Pacific Ocean on Jupiter's atmosphere, while in 2021, amateur astronomers captured footage of an unidentified object colliding with the gas giant. Situated immediately after Mars, Jupiter stands as the second planet after the Earth group planets. If this massive planet, with its formidable gravitational pull, had an irregular orbit, the configuration of the solar system would likely be drastically altered, potentially excluding human existence. Jupiter's motion is finely balanced, positioning it between the solar system's second most massive planets at both ends, exerting minimal gravitational influence on either. Each of these factors, individually and collectively, played a crucial role in fostering the conditions for complex life to emerge on Earth. Remove any one of these factors, and the emergence of humans would have been highly improbable. Numerous variables remain elusive beyond what the authors of Rare Earth have outlined, as they mainly address surface-level phenomena. For instance, Earth's unusually large core is a notable mystery. This peculiarity may be linked to our moon. When comparing Earth to other rocky planets like Mercury and Venus, which lack moons entirely, or even examining the Martian moons, Phobos and Deimos, which are irregularly shaped and more akin to captured asteroids than true moons. Phobos, with a diameter of 22 kilometers, and Deimos, with just 12, it becomes evident that Earth's moon is exceptional. Earth's moon is the largest natural satellite in proportion to its planet, comprising 27% of Earth's size. In contrast, even Pluto, once classified as a planet until 2006, is roughly 6 times smaller in mass than our moon. The formation of Earth's moon presents a puzzling conundrum. Analysis of lunar rock samples collected by Apollo astronauts revealed a striking resemblance in composition to Earth's crust. The prevailing theory, known as the Theia hypothesis, posits the existence of an ancient planet, roughly the size of Mars, which collided with Earth approximately 4.5 billion years ago. It's quite possible that we have 2 planets under our feet. That's why the Earth's core is so large. The debris from the impact formed our moon. So, satellite that big causes the tides to rise and fall? Darwin himself assumed that the first simple life was born in one of the basins that arose as a result of the tides of interaction of the moon. In addition, some scientists believe that after the emergence of life in water, its further spread from the ocean to land was also provoked by gravitational influence. This is not the tides we're used to. This is what the moon looked like in the sky 4 billion years ago. As you can guess, its gravitational effects were far more terrifying. That is, living organisms from the ocean were literally constantly being ejected onto land and dying until some turned out to have beneficial mutations. Data from 2019 suggests that they may have formed in the outer solar system, and most of Earth's water originated there. So perhaps those oceans you see don't originate from there. Rare Earth authors Peter Ward and Donald Brownlee point out that the Great Satellite increases plate tectonics, which is necessary for biodiversity and the carbon cycle. In addition, this giant impact gave the Earth its peculiar axial tilt and fast rotation rate. The rapid rotation reduces daily temperature variations and makes photosynthesis viable. According to the Rare Earth hypothesis, the axial tilt should not be too large or too small, because a planet with a large tilt will experience extreme seasonal climate fluctuations. If the planet has a small tilt, or if there is no tilt at all, then the planet will have no seasons. And this will lead to a lack of stimulus for evolution. From this point of view, the tilt of the Earth is optimal. The gravity of a large satellite also stabilizes the tilt of the planet. Without this effect, the change in tilt would be chaotic, which would probably make complex life forms on land impossible. You didn't hear that, by the way. Indeed, there are seemingly completely paradoxical factors. For example, twice in the history of the Earth, the temperature of the Earth has plummeted, and it has been completely covered by ice. 2.2 billion and 635 million years ago. These extreme glaciations favored the development of life. The first glaciation stimulated the development of photosynthetic microorganisms, which led to a strong decrease in greenhouse gases in the atmosphere and the release of oxygen. And after the second glaciation, the Cambrian explosion occurred, which gave rise to almost all of the evolutionary branches of animals that exist today. If before that, all life was simple and unicellular, after that, there is a sharp increase in the number of complex multicellular organisms. This is where the first brain appears. Think about it. If we find a planet in space with paradisiacal conditions, that's probably why we won't find complex life there. It's just not needed there. On a paradise planet, there are no complex survival tasks that need to be solved. As we can see, contrasts are needed to develop complex life. In what ratio? No one knows. Positive factors are not enough. They must be balanced by negative ones for the very stimulation of evolutionary processes. But at the same time, the negative factors should not be too negative, because life is a fragile thing, after all. How many factors should come together in the right sequence? Let's start small. Let's say we have all these habitable zones within a star and a galaxy. There are gas giant defenders, and there's a rocky planet with water, the right atmosphere and a large moon, an absolute twin of Earth somewhere out there in space. And what's next? Nothing. If you haven't watched my video From Atoms to Consciousness, I'll briefly explain that the first smallest brick we call life is a replicator. That is, a molecule capable of reproduction. Only with the emergence of the first replicator do the directed mechanisms of evolution begin to operate. But the first replicator itself must have appeared by chance. Think about it. A complex system, capable of replicating itself, must have appeared by chance. So we look for the simplest combinations from which this very first replicator could have emerged. But the simplest combinations we see are still very complex. So, what is the likelihood of the first maximally simple organism being able to reproduce? The recognized expert in evolutionary and computational biology, Eugene Koonin, in his book, The Logic of Chance, gives an estimate of the probability of spontaneous appearance of the first replicator. He gives a figure of 1 in 10 to the 1018th degree. You can pause and read his calculations on the screen. 1 in 10 to the 1018th power is 1 with 10 18 zeros. It is impossible to grasp in your mind how unlikely this event is. Eugene Koonin himself sees a multiverse as one of the explanations for how such a thing could even be possible. If there are an infinite number of universes, then there will be an infinite number of configurations of atoms. And in such a case, the realization of the variant with spontaneous appearance of the replicator is easily conceivable. But it would be very convenient to immediately explain such things by a multiverse or world will or God. So, Koonin reminds us that we should lower the bar as much as possible and explain by spontaneous emergence only what really cannot be explained otherwise. The emergence of life requires exceptionally unlikely events, and consequently, we are alone in our universe. Not just us intelligent beings, but more broadly, living beings in general. I don't want to dramatize, but I have to. Here we have the first replicator appearing and starting to reproduce. A very important question arises here. Is an increase in complexity mandatory in evolution? The answer is absolutely not. You see, some of the first replicators, the Prokaryotes, were bacteria and archaea. They were extremely inefficient. By design, they could not store energy in large quantities and become complex. There was no way around some kind of mutation. This is where evolution wasn't enough. A revolution became necessary, causing a billion-year halt in development at the prokaryotic level. There was no indication of more intricate life forms. Evolution could have ceased altogether, but then an unlikely event occurred. An archaeal cell engulfed a bacterium and failed to digest it. This bacterium, in turn, deactivated 99% of its genome, shed most mechanisms, and prioritized energy production, giving rise to the first mitochondrion, the cell's powerhouse, This symbiotic relationship, addressing the energy dilemma, facilitated the unchecked complexity of life. It is this improbable, microscopic event that ultimately led to the existence of all visible life forms. I hope no one has lost interest, as the most significant aspects are ahead. The number of intelligent civilizations in the universe is equal to the number of habitable planets multiplied by the probability of the origin of life, and then by the probability of intelligence among that life. However, the presence of intelligence is not guaranteed by these factors alone. While much of what we have discussed so far may seem abstract or theoretical, this factor can be observed here and now. Mankind has recorded over 1.7 million species of living organisms, but that is not all of them. It is estimated that there are about 8.7 million species on Earth today, and about 500 million species are extinct. How many of these species possessed intelligence is a separate conversation that we will not address here. You can learn more about what intelligence is in my previous video. Essentially, our grasp of rationality, intelligence, and consciousness is quite limited. We rely mostly on intuition. While our own existence suggests that intelligence can arise, the rest of life on Earth demonstrates that evolution doesn't prioritize intelligence. Moreover, the emergence of consciousness is highly improbable. Charles Lineweaver, a researcher, contends that intermediate stages in evolution don't always lead to certain outcomes, especially regarding extreme traits like intelligence. Big brains are no more inevitable than the long noses of animals like trumpet-toothed elephants, monkeys, whales, elephants, dolphins, octopuses, and squid, and are considered the most intelligent creatures on Earth, after humans. Dolphins in particular are very intelligent. Their brains are similar to human brains in many ways. But as Lineweaver notes, dolphins had about 20 million years to build a radio telescope, but they didn't. Why? Why the only so-called intelligent species on the planet? Are you not surprised that evolution, so economical in its manifestations, has created the human brain? A device with such a degree of redundancy that even now in the XE-century it perfectly copes with the problems of an advanced civilization. After all, anatomically and biologically, it is the same brain as the brain of our primitive barbarian ancestor who lived 100,000 years ago. How this enormous perspective mind potency, this redundancy, as if ready at the dawn of history to begin building civilization, arose in the course of a purely probabilistic evolutionary game of adding up two vectors, increasing mutations and increasing natural selection. What is probability? Each variable in the equation for counting intelligent civilizations in the cosmos implies many factors, which we have tried to enumerate. So what do we get? To some extent, we understand what it takes to make a planet habitable. However, we have little knowledge of what factors are necessary for the emergence of the simplest forms of life on such planets, let alone how those factors lead to the development of consciousness. While most of the factors remain unknown, let's indulge in a little daydreaming. Imagine we have a formula that guarantees a 100% probability of complex life occurring if 80 factors are met. A very optimistic scenario. Let's go even further and make the probability of each factor not 1 in 10 to the power of 1018, but only 1 in 2, which is like flipping an abstract coin with 0 thickness. In this scenario, every factor, such as finding a sun-like star or a habitable rocky planet, has a 50-50 chance of occurring. Even factors such as the presence of a moon-like companion or the appearance of the first replicator are considered a 50-50 chance. If all 80 necessary parameters were so, what would be the probability of encountering intelligent beings like us in the universe? The probability would be incredibly small. 10⁻24 degrees, or 1 in a trillion trillion. Simply put, even if you explored the entire observable universe, the chance of finding a single Earth-like planet would still be virtually nil. In reality, there are likely many more factors at play. Few of these factors are as optimistic as a simple flip of a coin. The claim that we are alone in the universe is self-serving and lacks solid evidence. We currently have no evidence, not only for the existence of extraterrestrial intelligent life, but also for life, in general, outside of Earth. Although the rare Earth hypothesis finds support among some popular scientists, it continues to be criticized, an example of which is the ongoing criticism of Peter Ward and Donald Brownlee's book. Recent studies and observations refute some of the assumptions. For example, while large moons are rare in our solar system, they appear more frequently around planets in other star systems. Arguments suggesting that they are necessary for the origin of life raise reasonable doubts. Moreover, a 2008 study found that Jupiter caused more collisions with Earth than it prevented, calling into question the idea that proximity to the star is the only means of maintaining a comfortable planetary temperature. The largest amount of water in the solar system may surprise you. It's not on Earth, but on Jupiter's moon, Europa, where there is twice as much. How is this possible? Europa's average surface temperature of -171 degrees Celsius is crucial. Tidal friction, caused by the eccentricity of the orbit of Europa and the gravitational pull of other moons, have created under a 30-kilometer layer of ice conditions for the existence of a huge ocean reaching a depth of 80 to 180 kilometers. Notably, the presence of organisms on Earth that can survive and reproduce in extreme conditions, such as tardigrades, suggests the possibility of life on Europa, despite it being outside the habitable zone. The fantasy also extends to Saturn's moon, Titan, where life could potentially be based on methane rather than water. Carl Sagan even allowed for the idea of non-water life on gas giants, like Jupiter. As we've observed, the rare Earth hypothesis suggests that the Sun seldom, if ever, traverses the spiral arms of the galaxy. However, astrophysicist Karen Masters has calculated that the Sun actually crosses large spiral arms, approximately every 100 million years. Moreover, some studies propose that certain mass extinction events align with previous passages of the solar system through galactic spiral arms. We're right in one of them right now, by the way. Doubt can be cast on nearly every aspect of this hypothesis. Most significantly, the rare Earth hypothesis exhibits an exceptional degree of anthropocentrism. It doesn't merely propose conditions for intelligent life. Rather, it outlines conditions specifically tailored for the emergence of humans. English astronomer David Darling's book, Life Everywhere, serves as a rebuttal to the rare Earth hypothesis. According to Darling, the rare Earth hypothesis is not a genuine hypothesis, but rather a selective interpretation of facts, crafted to explain the origin of life on Earth. What matters is not whether there is anything unusual here on Earth. There will be something different about every planet in space. What matters is whether any of Earth's circumstances are not only unusual, but essential to complex life. Given that we really have no idea what parameters and in what order should be in the equation, given that we have little idea what intelligence is and what it might be like, what makes us think the earthly option is the only possible option at all? Let's face it, we're not looking for all sorts of civilizations, but primarily anthropomorphic civilizations. We bring to nature the logic and order of the scientific experiment, and by phenomena of this kind, we long to recognize beings like us. However, we do not observe such phenomena, are they? Not there. Indeed, there is something deeply saddening in the silence with which the stars answer this question, a silence so complete as if it were eternal. The rare Earth hypothesis, if taken seriously, can indeed bring sadness or even fear of fundamental loneliness. But is it loneliness we need to fear? Launched in 2021, the James Webb Telescope will conduct an infrared study of the composition of the emissions from the geysers of the Europa geysers in order to confirm their aquatic nature. In the long term, we want to get samples of the emissions and study them. And if we find traces of life, even simple life, much less complex eukaryotic cells, this could be the most tragic news in human history. Thank you for watching.